Welcome back to the deep dive. Today, we're really moving far beyond just the chatbot.
Way beyond.
We're dissecting the brain, you might say, of synthetic intelligence that doesn't just talk, but actually thinks, reasons, and crucially acts on its own in the real world.
Right. Autonomously.
We're setting the stage for quite a dramatic shift. The focus is moving away from writing that complex, rigid, step-by-step code
Yeah, the old way.
towards building intelligent systems based on this really ambitious idea.
Hmm.
Understanding and basically copying how a human would reason through a problem.
Uh-huh.
The idea is, well, pretty simple on the surface.
Hmm.
If you can think it, the agent should be able to build it.
And, well, that idea is the core challenge, isn't it? Because right now, there's this massive performance gap. What we're exploring today is the architecture, the blueprint, that takes a powerful large language model, that brilliant text predictor everyone's using, and turns it into a truly autonomous agent, one that can actually solve complex, multi-step tasks. So our mission today really is to give you a shortcut to understanding this agent's mind. We're breaking down the 4 essential pillars: perception, reasoning, memory, and execution.
And the need for these systems, it's really highlighted by some, let's say, harsh realities out there.
Absolutely.
If you look at the benchmarks like Osworld that one test complex software automation, the results, well, they show just how far we still have to go.
Yeah, tell us about those numbers.
Humans get a task done correctly over 72% of the time.
Okay, that's the baseline.
While top LLM agents, they're still only hitting around, what, 42.9%?
Yeah, just under 43%. And that massive delta, that gap, it means current systems basically fail half the time when things get tricky.
Like what kind of tricky?
Oh, a pop-up window, a system error message, maybe just an unexpected step in a process.
Right. Stuff that breaks the script.
Exactly. So to bridge that 30-point gap, we have to perfect these 4 cognitive systems.
Okay, before we jump into those pillars, let's clarify something important for everyone listening. We keep saying agent. How is that really different from, say, a rigid, old-school automated workflow?
Ah, good question. Think of a traditional workflow like setting up a really long line of dominoes.
Okay.
It follows a preset sequential plan. Everything is designed upfront by the engineer.
Right, step A, then B, then C. No deviations.
Precisely. And if a single domino, maybe an unexpected error pops up, or a website changes its layout slightly, if anything's out of place, the whole sequence just stops, it crashes, it can't adapt.
So a true agent is the opposite, no rigidity.
It's completely dynamic. Its focus is the goal, not the sequence of steps.
Okay.
Like the agent figures out its own strategy as it goes. It constantly adapts based on what's happening in the environment. It uses complex reasoning to break down problems. And critically, it learns to recover from mistakes. It has autonomy. The workflow just doesn't.
Got it. Autonomy. And that's enabled by these 4 pillars: perception, reasoning, memory, and execution. Let's start with number 1, perception. This is the agent's gateway, its eyes and ears.
Exactly. This is where we make sure that the LLM actually understands its surroundings, its environment.
How does that work?
The perception system takes in raw stimuli, maybe images of a screen, system logs, maybe even sound, and it converts that raw input into something meaningful, structured, something the core LLM can actually process.
Okay.
And since most real-world tasks involve clicking around on screens, graphical user interfaces, we have to use multimodal LLMs.
MMLLMs.
It sounds incredibly complex. I mean, if these are just processing layers, how does a picture, just pixels, turn into something the LLM understands as, like, click this button or that's the checkout?
You're right, it is a pipeline. Think of it maybe like a 3-step translation. First, you've got the modality encoder, something like a vision transformer. It looks at the image and pulls out the visual features, the lines, the shapes.
Seeing the raw shapes. Yeah. Then, step 2, the input projector. This is the translator. It takes those visual features and aligns them, maps them into the abstract text space the LLM works with.
Okay, bridging the gap.
Exactly. And finally, that processed data goes to the LLM backbone. That's the core engine that does the actual thinking or reasoning.
Now, our sources point out that even with this pipeline, there's a big problem. Current visual models, they struggle with knowing exactly where things are, the spatial relationships.
Yeah, spatial precision is tough.
And they tend to hallucinate. Seeing buttons or objects that just aren't actually there, that sounds like a recipe for disaster.
Oh, absolutely. It's bad if your agent clicks on a submit button that doesn't exist.
Right.
That's the Achilles heel of just using raw vision. And it's why we have to rely on augmented perception. We don't just give the agent eyes, we give it guided interpretation.
How do you guide it?
Well, one really successful method, especially for complicated screens, is called set of mark. Some
Set of mark.
Hmm.
That's where the image gets annotated, right?
Yeah.
Like
Yeah.
highlighting a textbook for the agent.
Exactly like that. External tools are used to draw on the image, basically. Adding explicit markers, bounding boxes around buttons, labels on fields highlighting the key interactive parts.
Ah, I see.
This extra info tells the LLM, hey, pay attention, right here, at these coordinates. That's the login field. It cuts down on ambiguity massively.
But visuals aren't the only way. We can also boost perception using data that, well, we humans usually ignore, right? The structured stuff behind the screen.
Absolutely. Often the most valuable perception comes from what you might call invisible context.
Like what?
Like the accessibility tree, the A11Y tree. This gives the agent semantic understanding. It knows the role of an element, like button or link, its label, its state, like unread or active tab.
Okay, so it understands what it's looking at, not just where it is.
Precisely. And agents often use the HTML source code alongside the screenshot too, combining the visual with that structured semantic data that drastically minimizes hallucination. It grounds the agent in reality.
And finally, perception can also involve tools, right? Like the agent perceives the weather by running a weather API call.
Exactly. Or it perceives the contents of a file by running some code to read it. The output of the tool becomes the new state of the environment that the agent perceives.
Okay, which brings us very naturally to the second pillar, the reasoning system. So the agent sees the world, now it needs to figure out what to do next.
This is the planner. This system generates and optimizes the action plan.
And planning usually means task decomposition, breaking a big, hairy goal into smaller, manageable steps. What are the main strategies agents use for this?
Well, we can contrast two main approaches, based mostly on how they handle feedback.
Okay.
First, there are the interleaved decomposition methods. Think chain of thought, SUT, or react. These are dynamic. They adjust maybe one or two steps at a time based on immediate feedback.
So if step one fails, it stops, thinks, and fixes step two.
Exactly. They're pretty fault-tolerant for simpler things. But for really big, complex tasks or tasks with lots of constraints, we often need something more robust, like DPPM.
DPPM. Decompose, plan in parallel, and merge. Planning in parallel sounds much faster for heavy lifting. Give me an analogy for that.
Okay, imagine interleaved decomposition is like one architect designing a huge corporate campus, building by building, sequentially.
Takes a while.
Yeah. DPPM is like hiring 5 specialist firms, one for foundations, one for plumbing, one for electrical, etc., and having them create their sub-plans at the same time, concurrently.
Ah, I see. Division of labor.
Right. This parallel approach avoids those sequential bottlenecks and dependencies. Then, a final merge agent takes all those concurrent results and synthesizes them into one coherent global plan.
That sounds much more robust and faster. And speaking of robustness, we also see agents exploring multiple plans, not just going with the first idea.
Huh.
That's where tree of thought, TT, comes in.
2T is all about giving the agent options. Instead of just one linear chain of thought, it builds a tree structure. Each node in the tree is like an intermediate thought or a potential action step.
Like exploring different branches of possibility.
Exactly. It lets the agent explore multiple reasoning paths at once, running little mental simulations, if you will. Then it evaluates which path looks best at each stage, using the LLM itself to judge. It makes the final plan much less likely to fail because of some initial bad assumption.
This is where these systems start sounding genuinely intelligent. How does an agent actually fix its own mistakes? Without a human stepping in, how does that feedback loop work?
That's the magic of reflection. It's
Yeah.
absolutely critical for learning and for the agent to improve over time. Reflection means the agent performs a self-evaluation after an action fails.
Okay.
It figures out exactly where things went wrong. Maybe it used a tool incorrectly. Maybe there was a flaw in its logic. Maybe it misunderstood the goal. Then it generates insights on how to correct it or improve next time. It internalizes the failure, learns from it.
So it doesn't make the same mistake twice.
Ideally, yeah.
And I've read about something even more advanced.
Yeah.
Anticipatory reflection. What's that?
Think of it as the agent playing devil's advocate with itself. Before it takes a step, especially a tricky or risky one, it pauses and proactively thinks about what could go wrong. It runs a sort of pre-mortem.
Yeah.
considers potential failures and alternative solutions before acting.
So it catches problems before they happen.
That's the goal. This kind of front-loaded thinking significantly boosts consistency. It mitigates challenges before they blow up into actual execution errors.
Now, to scale this kind of complex reasoning, we often hear about multi-agent systems, different specialized LLMs working together, like a team.
Yeah, forming a cognitive team is often necessary.
Who are the key players on this AI team?
You definitely need specialists. You've got your core team. The planning expert does the decomposition and strategy. The reflection expert handles the postmortem, the learning from mistakes. And the memory management expert deals with context and information retrieval.
Okay, makes sense.
But maybe the most practical day-to-day expert is often the error handling expert.
What does that one do?
This one diagnoses one-time problems, like it realizes an item it needs isn't visible on a web page.
Sure.
And then it proposes a specific fix, like try scrolling down or maybe refresh the page. It handles those common little execution snags.
Very practical. Okay, moving on to pillar 3, memory. An agent can't be a useful partner if it forgets everything the second you close the chat window, right?
Okay.
It needs to remember things.
Absolutely. This is fundamental. If you want an agent you can build a relationship with, one that learns about you. The big challenge is long-term memory.
How do they achieve that?
Well, a cornerstone technique is RAG, Retrieval Augmented Generation. Think of it as giving the AI an open book test. Instead of just relying on its internal knowledge, which might be outdated or incomplete.
Like its training data cutoff.
Exactly. The LLM queries an external verifiable knowledge base, could be documents, emails, databases, websites, and pulls that fresh, relevant info directly into its reasoning context for the current task.
And that helps with?
It drastically reduces hallucination, the model making stuff up, because it's grounding its answers in real, retrievable data.
So AG is about pulling in external info. But what about knowledge stored inside the model itself, learned stuff?
Correct. That falls under embodied memory. This is more about experiences, skills, and behaviors that get encoded directly into the model's parameters, usually through ongoing training or fine-tuning. It's more like ingrained, almost unconscious knowledge.
Like muscle memory, but for an AI.
Kind of, yeah. And then for really precise structured data like customer records or inventory, the LLM uses structured knowledge systems. It learns to generate SQL queries using text to SQL to reliably pull data from traditional databases.
Okay, so if the agent is constantly learning, reflecting, retrieving, what kinds of things does it actually store in its memory to get better?
Good question. It mainly hoards 3 key types of data. First, experiences. It logs both successes and, crucially, failures. Explicitly logging failures helps it avoid repeating them.
Smart. What else?
Second, procedures. These are like reusable routines or generalized workflows it learns from tasks it did successfully before. Think of them as saved recipes for common jobs, sometimes called agent workflow memory or AWM.
Okay, experiences and procedures. And the third type sounds really important for personalization.
It is. That's user information. Systems like Memory Bank are designed to synthesize and store details about the user personality traits inferred from chats, past requests, preferences, maybe even emotional tone.
Wow.
This lets the agent adapt how it interacts, tailor its suggestions over time. It moves from being just a generic tool to, hopefully, a truly personalized collaborator.
So memory isn't just about facts. It's about building a persistent, adaptive identity for the agent.
Exactly.
Which brings us finally to the execution system, pillar 4. This is where thoughts turn into action, where the plan actually impacts the real world.
Yep, the action phase. Execution usually starts with the agent using external systems through tool or API integration. It generates a very precise, structured output, often JSON saying exactly which tool to use and how. Send this email, query that stock API, make this web request. But the real power for automation, especially with GUIs, comes from multimodal action spaces.
Meaning it can actually, click and type on the screen, like a person.
Precisely. Visual interface automation lets the agent generate specific mouse clicks, keyboard inputs, drag and drop actions, even when there's no official API for the software it's using.
How does it know where to click?
It uses that enhanced perception we talked about, the set of mark annotations, the accessibility tree info, to accurately target pixels or elements on the screen and interact with them.
Okay, that's powerful. And maybe the most flexible tool in its entire kit, giving it almost unlimited potential, is code itself.
Indisputably, dynamic code generation and execution. The agent can write its own Python scripts to analyze complex data, generate SQL for database work, or whip up shell scripts for system tasks.
So it can write its own tools on the fly.
Essentially, yes. The ability to write and run its own code means its potential actions are really only limited by the systems it has permission to access.
Okay, wow. Let's zoom out then. We've walked through perception, reasoning, memory, execution. Can you quickly synthesize that whole cognitive loop for us?
Sure. If you picture it, it's a continuous cycle. Perception gathers info from the environment. That info feeds into reasoning, which uses memory to figure out a plan. The plan triggers execution, the action. That action changes the environment, which then feeds back into the next round of perception and often reflection to learn from the outcome. It's a constant loop.
That's the blueprint for hopefully getting towards that 72% human-level performance. But let's be real. We started by mentioning that 42% agent success rate.
Right.
What are the big roadblocks right now? What's holding back mass adoption?
Yeah, good point. We face two major hurdles, I'd say. First, cost and time. It takes enormous resources, compute power, data, time to teach agents these complex experiences and constantly fine-tune that embodied memory.
Especially since many top models are closed source.
Exactly. That makes custom fine-tuning really hard or impossible for many users. Second, despite all the tricks like set of mark, visual perception accuracy is still a nagging problem. Small misreads of the screen can easily lead to bigger failures down the line in reasoning or execution.
Okay, so cost, time, and imperfect vision are the main friction points today. Looking ahead then, what's the big dream here? What's the next generation of these agents aiming for?
Well, the immediate big goal is moving beyond that expensive, slow training process. The aim is to get agents to learn a complex task after watching a human do it just once, the learn from one shot idea.
Learn from a single demo. That'll be huge.
It would. But the most ambitious extension, the really far out research direction, flips the whole script.
How so?
Instead of humans being assisted by AI, the goal is to develop systems where humans act as assistants to the LL agent.
Wait, humans assisting the AI?
Yes. The human only steps in to provide specific clarification or maybe some niche expertise when the agent gets stuck. The ultimate goal is to boost overall human productivity on really complex real-world work by potentially 10 times.
Yeah.
It means shifting the entire burden of managing and executing the task onto the AI, with humans just providing high-level guidance or specialist help when needed. That's the long-term vision.